is Lili Alderson. Lili is a final year PhD student at the University of Bristol, where her research involves observing and interpreting exoplanet atmospheres across the mass range with space-based telescopes. Lili completed her undergraduate degree at the University of Southampton, spending a year in research at the Center for Astrophysics, Harvard and Smithsonian, and in September will be joining Cornell University as a Klarman postdoctoral fellow. Her talk today is entitled Observing Atmospheres Across the Radius Valley. And I still read that very quickly. But I think, you know what, let's just get started. Lili, go ahead and take it away.
All right. Thank you, Tiffany, for the introduction. Yes, today I'm going to be telling you about some early work from the JWST Compass program, including actually a paper that was accepted like 4 hours ago. So hot off the press, let's get into it. So wouldn't be an exoplanet talk without our wonderful mass separation diagram, as always, as you can see here. And if you kind of take a look at this, what sort of immediately jumps out is that our exoplanets don't look that much like our solar system planets. Part of this is because we're biased by our detection methods. We know that transits are much better at finding things closer into the stars. And so we just don't quite probe that same parameter space that the solar system exists in. But there are some things that are a little bit weird that we just don't simply see in our solar system. This includes our hot Jupiters. So these are Jupiter-sized planets which orbit very, very close to their stars. And so they are very, very hot, hence the name. And we've gotten very good at kind of analyzing the atmospheres of these planets. And then we also have kind of in between the Neptune and the Earth-sized planets, or Neptune and Earth that we see in our own solar system, we have this kind of huge cluster of planets that sit in that kind of parameter space that we don't have an analog for in our solar system. Inventively, we call these things the sub-Neptunes and the super-Earths. And if we peer into this population in a little bit more detail, what we see is that actually the sub-Neptunes and super-Earths are two slightly more distinct populations. We have what's known as the radius valley. So if you take the size of the planets versus the occurrence rate, you see that you kind of get this double peaked feature. So you have a peak of things a little bit bigger than Earth, and then you have a peak of things that are a little bit smaller than Neptune, with a sort of dearth of planets in the middle. And right now, it's not entirely sure what exactly is causing this radius valley. We don't really know how it got there. And there are many kind of suggestions, perhaps things that started out in the radius valley, then shift down towards lower sizes because they're losing mass, they're losing their sizes because of photoevaporation, maybe core powered mass loss. Perhaps there's just an intrinsic difference in the population, and this is just what happens when you have a large amount of planets. It's kind of in this unknown parameter space right now where we have this population, but we don't quite know what's causing it. And kind of with our density and our mass measurements, there's only so much that we can do to understand what's going on here. But really, it's atmospheres that can help us to sort of get some more clues and understand in a little bit more detail what's going on. So the compositions of mini planets for atmospheric statistical study program, or the COMPASS program, is designed to build that link between our planetary demographics that we have right now, which show the radius valley, versus that atmospheric characterization that hopefully can peer into that parameter space in a little bit more detail. So our program is observing 11 exoplanets in transmission using JWST NISVEC G395H. That gets us spectra from about 4 to 5 microns. And the total sample that we have is going to include 12 planets, so an additional planet that's part of a GTO program, and we'll have in total 4 pairs of planets that are in the same systems of each other, so 4 multi-planet systems. And overall, the aim is to try and measure kind of these major molecular species that we expect to see within these atmospheres, and try and see if we can get some insights into perhaps the formation pathways and how these planets might be evolving and understand what might be going on. And part of the aim of this program is our sample has been selected through this statistical manner, such that hopefully we should be able to draw conclusions about the wider small planet population rather than just our sort of 12 planet sample. So our sample looks something like this. You can see here all of our planets are smaller than 3 Earth radii, but we span that radius valley parameter space. So we've got both sub-Neptunes and super-Earths. We're also spanning that mass range as well. And in terms of equilibrium temperature, we're going from about 400 Kelvin up to about 900 Kelvin as well. You can see that through the colors on this slide. And today I'm going to talk about two of the planets, which have been highlighted with these little circles here. And these actually were the first planets that were observed as part of our sample. So the TOI 836 system consists of two planets, a super Earth and a sub-Neptune, both orbiting a K-dwarf. So the super Earth, which is TOI 836b, is about 1.7 Earth radii, so it's kind of on that lower edge of the radius valley there, and is about 800, 900 Kelvin. The sub-Neptune TOI 836c is a little bit further out, a little bit cooler, a little bit bigger. And so we've sort of got these two individual planets in our system that we're both observing through our program. I'm going to mostly talk about TOI 836b today, but I'll also focus a little bit on TOI 836c as well. So why do we care about this system? Well, in part, as I said, it's the first data that we got, but also this system is sort of either side of the radius valley. Because here we've got two planets, which are one is a sub-Neptune, one is a super Earth, they're both orbiting the same star. This allows us to kind of control for the stellar environment that they're existing in, and hopefully maybe start to disentangle, or at least we can rule out some of the influences. We can say, you know, both of these stars are, or both of these planets, I should say, are experiencing the same kind of UV flux, that kind of thing. Maybe we can start to understand a little bit more about what's going on. So how do we do that? How do we measure these atmospheres? Well, Compass Survey is using transmission spectroscopy. We observe our planet as it passes in front of its star, and we can measure its transit depth. But if that planet has an atmosphere, what we see is that at different wavelengths, different parts of the atmosphere, different molecular and atomic features are going to be absorbing different amounts of light. And so we see that the transit depth, the radius of the planet, is changing. And if we observe many wavelengths with our spectroscopy, so in this case, using JWST NIRSpec, we can get the transmission spectrum of the planet. So in the bottom right here, this is a very typical hot Jupiter transmission spectrum. You know, you've got your big water absorption features in the near infrared. You've got sodium, potassium. This is not the kind of thing that we're expecting to see necessarily for a super Earth, but it does give you an idea of what a transmission spectrum in general looks like. And as I said before, we've gotten very good at doing these hot Jupiter light transmission spectra. Small planets are a very, very different story. So on this slide, I've got super Earths, purple, and hot Jupiters in blue. The circles here represent true sizes of a real super Earth and a real hot Jupiter. And then we've got some real NIRSpec data taken of those two corresponding planets. As you can see immediately, super Earths are very, very small compared to our hot Jupiters, and we have a much, much smaller transit depth that we have to try and deal with here. It's much harder to observe what we want to see. We also have this added complication, or there may be advantage in some respects, that our super Earths tend to be orbiting much, much brighter stars than our hot Jupiters. This is normally because they are test targets and test preferentially observes bright things. That's very helpful in terms of making sure that we have enough atmospheric signal that we can expect to see something using this transmission spectroscopy method. But that has the added challenge that our cadence has to be very, very high to avoid saturating our telescope. In fact, many of the compass planets and many of the small planets being observed with JWST in its first couple of cycles are really, really close to the brightness limits of our detectors. And so we have this very, very high cadence, which complicates things when it comes to our actual observations. So as you can see here, these are, again, real data of some of the planets in the compass sample. And we've got some instrument systematics that we need to be dealing with. So NIRSpec consists of two detectors, NRS1 and NRS2. I'm showing NRS1 light curves in the top panel and NRS2 light curves in the bottom panel. And you can immediately see that these two things don't look the same. This is not an astrophysical effect. This is an instrument systematic, which is occurring here. So we generally tend to see that these slopes that we're seeing, particularly in NRS1 across our entire visit, are stronger for our brighter targets than they are for our dimmer targets. And as I said, these two detectors aren't quite behaving in the same way. NRS2 isn't totally free from systematics. There's still a little bit of a slope there. You can sort of squint if you can see it in the purple dots there. Maybe these differences are because the two detectors aren't quite used as frequently as each other. Maybe something else is going on. We're not quite sure yet what the exact cause is, but we can still analyze our data and get some good results. So jumping back to 20836b, we observed 2 transits of this planet back in March of 2023, so almost exactly a year ago, actually. And for all of the planets in the COMPASS survey, we are analyzing our data with at least 2 independent reduction pipelines. In this case, we used Exotic Jedi, which is a pipeline that I have developed throughout my PhD. And we also used Eureka, which is a community-developed pipeline. So you can see here in the top panels, I've got our light curves from visit 1. In the bottom panels, I've got our light curves from visit 2. And again, you can see that difference between the 2 detectors and the 2 different shades of purple here. Once we've fitted our light curves, we can then move on to our transmission spectrum, which looks something like this. Again, we've got 2 different visits shown in the 2 different colors. Jedi on the left-hand side in purple and Eureka on the right-hand side in green. In general, the spectra from the 2 different visits agree pretty well. Median differences between them are kind of comparable to our average transit depths uncertainties for these individual visits. So that's a good sign that at least we're not seeing perhaps any stellar activity that are different between the 2 different visits. But the reason you take 2 visits is to try and narrow in on your precisions, have more precise transmission spectra so you can try and peer into those features in a little bit more detail. So our combined transmission spectrum for this target looks something like this. So you can see here again, Jedi in purple, Eureka in green, and we've got that difference between the 2 in that bottom panel. So immediately you can sort of see there's no obvious big stellar features jumping out here, even with our kind of improved precisions of combining 2 transits. But at least we do have consistency between our 2 reductions here. So the median difference in this case of about 10 ppm compared to our median transit depth uncertainty of 25 ppm. So that's good. We want to see the difference between our pipelines is smaller than our uncertainties. We can say that these 2 things are consistent, even if we're not necessarily seeing any big features jumping out at us. So we ran some very, very simple tests just to see, this looks like a flat line. Is it actually a flat line? Or is there, there's not any offsets between our 2 detectors? Are there any slopes, that kind of thing? So we fitted for a flat line, an offset, and a slope, and we found that for this data set, the flat line was kind of that 0 slope line, as I should say, is the best fit in this case. But we can still do some interesting science and explore what's going on here with some models and try and get some constraints on our atmosphere. So we used some Picasso models, which you can see on the left-hand side of the screen here, to try and understand what might be fitting this atmosphere, and can we rule out any particular scenarios in this case. So on the left-hand side, as I said, we've got Picasso models going from 1 times solar to 1,000 times solar metallicity. We've got the chi-squareds there, and then also sigma values, which tell you sort of how well we can rule out that model in general. If something is higher than 3 sigma, we say that we can rule that out. On the right-hand side, I then sort of got this plot demonstrating how across metallicity values and the corresponding mean molecular weights at the top, we can rule out different scenarios. So again, anything above 3 sigma, we're ruling out. Anything below 3 sigma is sort of a potential scenario for this atmosphere. So very obviously, we're ruling out these sort of low mean molecular weight, puffy, hydrogen helium dominated atmospheres in this sort of 2.2 mean molecular weight, kind of 8 to 7 rule out sigma regions. And for our joint visits, so where we've combined our 2 different visits in these thick weighted blue and red lines, we're able to rule out atmospheres below about 250 times solar metallicity. So anything above 250 times solar metallicity is statistically possible for this planet. But as you can see here, we do get this improvement when we go from our our individual visits, so visit 1 and visit 2, in sort of the dashed and the dashed dotted lines, compared to what we get for the weighted and the joint visits. So we know that you can get better constraints when you add in an additional visit and you take that combination. And so we wanted to see, okay, right now we're able to rule out, going from 1 visit to 2 visits, we're going from ruling out 100 times solar metallicity to about 250 times solar metallicity. How many more visits given this improvement that we see in our data, would we need to rule out perhaps an 1,000 times solar metallicity atmosphere? So here we've got a grid of those values. You can see metallicity down the bottom, and now we've got apparent surface pressure as well as our y-axis. So this is essentially just saying like a cloud deck, but kind of degenerate with these sorts of atmospheres. It's unclear whether sort of the opaque layer of an atmosphere is a cloud deck or there's actually just a solid surface. So we're calling it an apparent surface pressure. So you can see here that to get to that sort of 1,000 times solar metallicity value, we would need 8 more transits than the 2 that we already have if we wanted to distinguish between what we can do right now and that sort of 1,000 times theoretical aim. But we also wanted to compare the improvements that we get given our sort of real data and see whether that was matching what Pandexo, which is a predictor tool, is sort of estimating would be a good observing strategy for this target. And what we find is that for some scenarios, Pandexo tends to be a little bit too optimistic in predicting the number of transits that would be needed to really robustly constrain those very high metallicity atmospheres. So sort of at that long metallicity of 3, so about 1,000 times solar metallicity, you can see that we're needing, in theory, a few more transits when you compare what the expectations would be for based on our real data, based on what Pandexo might want to tell you to do. And so we sort of tentatively recommend that anyone who might be planning a future observation, particularly of a small rocky-ish planet, especially around a bright star, might want to be a little bit more conservative in kind of the precisions that they might be suggesting they might be able to achieve, or perhaps ask for 1 or 2 more transits if you're particularly keen on getting really, really tight constraints on kind of 1,000 times or 500 times solar metallicity values. All right, enough about the super Earths. Let's have a quick look at the sub-Neptune, TY836c. So I won't show the light curves in this case. They pretty much look the same as they do for the other planet. The transit depth's a little bit bigger because the planet's a little bit bigger, but we're around the same star, so we have all the same noise properties. Taking a look at our transmission spectrum, in this case, we only observed 1 visit of this planet, a little bit bigger, and so we just didn't need those 2 visits to get the constraints that we wanted. In this case, we're getting a median difference of 16 ppm between our Jedi, again in purple, and Eureka in green reductions, compared to our median transit depth uncertainties of 35 ppm. So again, good agreement between our 2 reductions, but you can sort of see there's a little bit of an offset perhaps between what we're seeing in the 2 detectors. So again, we did that very simple modeling. We fit a very simple 0 slope line, we fit a slope, we fit an offset, and we do find that there is a little bit of a step between those 2 detectors in this case. So for the rest of the modeling for this planet, we fit for an offset before we fit the models to the observation. And that's something that's been seen in quite a few other planets, particularly these very, very small things that are around very, very bright stars, where our noise properties right now are a little bit complicated and we're not 100% sure what's going on. So back to our Picasso models for this planet. Again, on the left-hand side, I've got 4 models. This time we've got from 10 to 1,000 times solar metallicity. We've also got a 100% H2O model, just because that kind of seems like it's a possibility given the size of this planet. On the right-hand side this time, rather than just having metallicity values, our sort of rule out versus possible solutions. I've now realized solutions is spelled wrong, but never mind. You can see here that we're now in sort of this 2D space. So the coloring is telling you what sigma we're at. So about 3 sigma is sort of this orangey yellow color. And up the y-axis, we've instead got that opaque pressure level again, or that apparent surface pressure that I was talking about. You can just sort of assume that that's consistent with a cloud. So the higher up the plot you go, the higher up in the atmosphere a cloud is being lofted to. In this case, you can see that in general, we're able to rule out metallicities closer to about 175 times solar. You can sort of see this kind of dark red region on the right-hand side of the plot. But there's also this teeny tiny little orangey red possible solution region right at the very, very top, where we've got 1 times solar metallicities and this really, really high cloud. So if we have a cloud or some kind of aerosol species between 0.1 and 1 millibar, potentially we could be having a solar metallicity atmosphere. And we ran some microphysical cloud models that actually show that, yes, potentially a cloud could be lofted that high in this atmosphere and it could sustain there. So this scenario, this kind of one-time solar metallicity, very, very high cloud, is possible for this planet. So back to the system as a whole, as I said, the aim of COMPASS is not just to look at individual planets, but it's to look at the broader population. So we've got our planets here with the stars plotted against the kind of broader population of similar sized planets, and some interior models for bulk hydrogen and helium mass fraction and bulk water mass fraction on the right-hand side. So for TOA 836b, based on the modeling that we have done of the atmosphere and also the models that you see on this slide here, we're pretty confidently able to rule out that it does not have a hydrogen helium dominated atmosphere. But potentially, if it formed with a hydrogen helium dominated atmosphere, if it had that sort of primordial hydrogen helium envelope, it would have likely lost that throughout the course of the planet's lifetime based on the insolation flux, based on how old the system is. So that's not to say that the planet has always looked like this. It's not to say that the planet definitely had a primordial helium envelope. It's just to say that the formation history of this one is a little bit uncertain. TOA 836 on the other, 836c on the other hand, potentially could still retain a primordial hydrogen helium envelope, and it could still have something of a hydrogen helium envelope right now, given what our atmospheric observations are showing. And you can see on the right-hand side, again, this sort of steam atmosphere scenario is also potentially possible for this planet. So some key takeaways. Small planets with JWST are going to be challenging. It's not going to be a walk in the park, but that doesn't mean that we can't still get some really great constraints on these atmospheres. For bright hosts and the small signal sizes that we're seeing, we are going to have to deal with more complicated systematics than we do for our hot Jupiter planets, but certainly nothing like what we were seeing previously with Spitzer and Hubble-based observations. And if you're planning for a similar program like this, if you want to look at kind of super Earths, particularly around very, very bright things, you might want to consider kind of thinking a little bit more carefully about the constraints that you're saying you might achieve, potentially even requesting 1 or 2 additional transits than what you might originally consider asking for. So for TOA 836b, which has been accepted as Alderson et al., should hopefully be on the archive very soon, we see that we do not find that the atmosphere is hydrogen helium dominated, and we can rule out metallicities lower than 250 times solar. And then for TOA 836c, which is a paper currently under review, led by a postdoc in our program, Nicole Wallach, we find that this planet could have a hydrogen helium dominated atmosphere, especially in the presence of these very highly lofted clouds. But at more reasonable cloud pressures, we can rule out metallicities less than 175 times solar. So hopefully, as I said, you should see these papers on the archive very, very soon, and more results from COMPASS will be coming in the coming months and across the next year. And with that, I'll take any questions.
All right, thanks so much, Lily. Again, feel free to use the reactions in the chat if you'd like to express your support that way. So again, if anyone has any questions, I'm taking a look at the chat, or feel free to use the raise hand tool to ask a question. All right, I see another one from Aviv. Go ahead.
Yeah, hi. Thanks, Lili. This was interesting very much. Thank you. I would like to ask, you were talking about the systematic effects of the data, and you had 2 visits of the small planet. How did the scaling go? As in, did the information by observing 2 transits actually scale by square root of 2, or was it worse? How far are we from Gaussian? How far are we from Gaussian data?
Yeah, so for TOA 836b, which was the one that we had the 2 visits for, we found that our improvements were something like 95% of sort of that square root scaling. So very, very close, but not quite. And we think that's probably because there's some amount of kind of noise that's left in the data that we're just not quite sure exactly how the best way is to handle right now. It's a new instrument, and we're still learning like exactly what is influencing the different things that we're seeing in our light curves.
Okay, thanks.
All right, a question from Hannah Wakeford. How does temperature play a role in the expectation for these atmospheres composition, especially given the metallicity constraints you have obtained?
Yeah, so a great question. So kind of let me jump back to, well, I ended the slideshow. Never mind. If I jump back to this slide here where we've got the temperatures for this parameter space, you can see that we're sort of ranging from this kind of 400 to our hottest ones are kind of 1,000-ish Kelvin. And we know kind of from literature expectations that a lot of planets in this temperature range are often cloudier than they are. We've seen recently that things that are more like 250 Kelvin have these very big features, even when they're sort of sub-Neptunes. And so it's quite possible that for many of these planets, there is this kind of cloud consideration, and that these atmospheres are hazier and cloudier than their much hotter and much colder counterparts. So that is something to take into account when you're kind of considering, just because something's a flat line doesn't mean there are no features in the spectrum. It may just be that these atmospheres have a lot of clouds going on, but the clouds are cool too.
Yeah, agreed. Clouds are cool. All right. Other questions? I do have one, but I'll keep an eye on that. Okay, nothing yet. So I guess just given, because these are 2 planets per single system, right? So do you have, I guess, given the amount of information you have, can you speculate on how you think the system might have formed, given the the observational constraints that you do have?
Yeah, not really my area of expertise.
Sure.
I think it's certainly for the if I jump ahead to, see, we've got to watch this animation. If I jump ahead to, and I ended the slideshow again. I'm so good at this. Okay, if we jump ahead to our system parameters, so you can see that like for TOI 836b, the smaller one, its kind of density is pretty much consistent with Earth-like, right? So it would be, I would be surprised if these 2 things looked the same when they first formed, and one of them has somehow suddenly changed dramatically, given that they are both pretty much experiencing, that one is on a 4-day orbit, one is on an 8-day orbit. So the insulation flux that they're receiving is fairly similar. So, I don't think it's the case of sort of 2 twin planets that have dramatically diverged. But I would be wildly speculating if I said anything more detailed than that.
Sure. Yeah. I was just curious. Okay. All right. Any last questions? All right. Well, congrats on the paper being accepted. That's very exciting. Very much hot off the press. Look forward to more stuff from Compass. So yeah, thanks again, Lily. And thanks again, Alex, for a great talk. All right, let's close here. Thanks again. And we will see you on April 12th. This is the week, I guess, of the eclipse, so that Friday, where we'll have Daniel Yahalomi from Columbia University and James Mang from UT Austin speaking at that event. So we'll again see you on Zoom. See you on April 12th. Thank you guys so much. Have a good afternoon, good evening, and talk soon. Take care, everyone. Thanks.